In this video, we're going to look at Aerodiazoniums. Now, what's an Aerodiazonium? Well, it's this guy right here. You have a phenyl ring with a N plus triple bond N on it. As you can imagine, this looks like a really good leaving group because if you can lose N2 gas and leave behind a positive charge, you have a really powerful carbocation which can react with almost anything and give all sorts of substitution products. Now, these things are moderately stable, so you can isolate them and keep them as real intermediate compounds. But first of all, we have to make it. And how do you make it? Well, you make it through a reaction of an amine, in this case aniline, with nitrite. You usually use sodium nitrite and HCl. So let's see how this reaction works. You start off by doing a reaction between the nitrite and the HCl. So let's just do that. So we duplicate the nitrite. Okay. Draw a reaction arrow. Duplicate the HCl, and of course the first step is simply we're going to protonate the nitrite. You kind of expect that to happen. So we protonate the nitrite, kick out a chloride, and we have now nitrous acid. Now nitrous acid is a pretty weak acid, and as a matter of fact the HCl is strong enough to protonate it a second time. So we're simply going to bring in a second proton. Okay, and protonate it again, and this is you probably guess what's going to happen next. We're setting ourselves up to lose a mole of water. So let's go ahead and get that product. And so now we're going to lose a mole of water. And of course, when we kick out the water, okay, if we just did this, that would leave that nitrogen electron deficient. So one of the two lone pairs on this oxygen swings around here, and it forms a triple bond. So here's our reaction. Let me make it a bit smaller so it gets everything on the screen. So this right here, NO+, that's the reactive species. Now that NO+ is going to react with the aniline. So let me grab the aniline, come down here and start over, and this is going to react with the NO+. Let me just redraw it so it's at a straight angle, triple bond, okay, and a positive charge on that oxygen. So this NO+ is going to be attacked. It's a cation. You expect that something of a lone pair might attack it, and indeed that aniline will come in, attack the nitrogen, okay, push one of the triple bonds out onto the oxygen, and we have our next intermediate. Now what's required next is just some kind of rearrangement of the protons. So one of these protons is going to be transferred over and back onto the nitrogen. So we're just an internal proton transfer, and once we've done this, we're here, and now this is a little more complicated. We've got to we're gonna lose the proton here, and again set us up for well, we're getting rid of that positive charge and set us up for losing the oxygen. So this simply comes in, forms a double bond here, and of course in doing this, we've got to push these electrons onto the oxygen, and see if we have room for this one. Almost. Let me just move things over a little bit. I don't really want to make it smaller. Okay, so here's this intermediate. Now what we're going to do is simply protonate that off. So we're going to come back and we're going to use another mole of HCl. Duplicate, grab the HCl, duplicate, grab the HCl, and we're going to protonate the oxygen, and here's our setting us up for our final reaction. Again, let me just get that on the paper. I could make it smaller and get it on the paper, but I don't want it too small. You won't be able to see what I'm doing. And so now we're going to lose that water, And of course, to kick out the water, we have to take the lone pair on this nitrogen, move it into triple bond position, and then kick out the water. And this will give us our final diazonium. And this is a lot of work in terms of drawing it out, but the reaction is actually very straightforward. So we can make these diazoniums starting with nitrite, HCl, and the aniline. Now let's see how these things react. So I'm going to erase all this stuff and switch programs. I'm going to go home, go back to Oscar Sin, where I have the program already loaded, and let me just center things a little bit here. Now, what can these things react with? Well, they react with all kinds of things. If we go to our reagent chart, we're going to see some of them. Starting over here with, there's a bunch of copper salts: cuprous oxide, cuprous chloride, cuprous bromide, cuprous cyanide. All of those things will react with a diazonium. Why copper? Well, copper actually helps catalyze the reaction. As you can imagine, that diazonium is very, very reactive. And if you just throw in other sources of reactants, you can actually get explosive reactions and things like that. So the copper helps moderate the reaction. But you can choose any of these things. Let's say the cuprous cyanide, simply because my mouse is sitting on it. So we add that, press the magic button, and we get a nitrile. What else can we try? We can go in, we try Ki. We don't have any other way of making aryl iodides conveniently. So here we go. We make the iodide. What else do we have on here? This, of course, this is the chloride. That's the bromide. What about this guy here, cuprous oxide? Can you guess what this is going to be? Well, cyanide, cuprous cyanide made the cyanide. Well, we have an oxygen there. Well, it's going to give the phenol. So there you go. The only one other one of interest, let me just clear up some room by getting rid of this stuff, is if you look in here, we have this one here, which is this strange phosphoric acid, but this is actually a hydride donor. And if you click here, whoops, what happened? Oh, I did it already. You actually, this furnishes a hydride, and a hydride substitutes for the dinitrogen. So dinitrogen is the other product from all these. So anyways, you can imagine these diazoniums can be very, very useful in synthesis and putting on all kinds of weird groups which you don't have any good way of doing otherwise.